Okay, picture this. You're on a beautiful, clear day at the coast, or maybe by one of the Great Lakes. The weather is perfect. Then all of a sudden, the water level just drops fast. And then this massive, unexpected wave comes roaring back in. It looks exactly like a tsunami. But here's the kicker. There was no earthquake. Nothing. So what on earth is going on?
Well, that's what we're diving into today. We're talking about meteotsunamis. They're essentially tsunamis, but they're generated purely by the weather. And what's really fascinating is just how much we're still learning. Get this, only about 3% of historical tsunamis are confirmed as meteorological.
Wow, just 3%. That suggests we could be, completely misclassifying a massive natural force. So if it's not an earthquake, what is the actual mechanism? What creates that initial, wall of water?
It all starts in the atmosphere. You can think of a storm system acting like a giant plunger on the water's surface. Immediate tsunamis are generated by these really rapid, significant changes in barometric pressure. Things like squall lines or severe thunderstorms. When that low-pressure system moves across the water, it literally displaces the water below it.
So it's not a sudden jolt from the seafloor, but more like a bulge or a ripple caused by the air pressure. But how does that small ripple turn into a genuinely destructive wave? This is where it gets really interesting.
Right, and the answer is resonance. This is the critical amplification factor. The wave size gets a huge boost, sometimes exponentially, if the atmospheric disturbance is moving at the exact same speed and direction as the wave in the water.
Oh, I see. So it's like pushing a kid on a swing.
Exactly. You don't need a huge shove every time. You just need to time your small pushes perfectly with the swing's rhythm. That perfect timing is what turns a small pressure ripple into a massive, powerful wave train.
And I'd imagine geography plays a huge role here, too. The shape of the coastline must turn the volume up even further.
It absolutely does. Coastal geography can act like a funnel. Things like shallow continental shelves or these long, narrow V-shaped bays. They focus all that incoming energy. The water has nowhere to go horizontally, so the wave just shoots up. We're talking about waves over 6 feet, and in extreme cases, much higher.
How high are we talking?
Well, the record was in Vela Luka, Croatia, back in 1978. They saw a nearly 6-meter wave. That's almost 19 feet.
19 feet. That's incredible. And given that they don't need an earthquake, I was genuinely shocked by how often the source material says these happen.
Oh, they're surprisingly common. NOAA data suggests about 25 immediate tsunamis hit the U.S. East Coast every single year.
25 a year.
And that's nothing compared to the Great Lakes. They average around 126 occurrences a year. You can see how global this is just by the local names they've been given over centuries. Risaga in Spain, Morobio in Italy, Abiki in Japan.
It really shows that people living near these geographic traps have been dealing with them for a very long time.
They have. And that's often led to confusion. These waves are often misidentified as something called a seisha, which is more of a sloshing wave in an enclosed body of water. To tell them apart, you really need accurate, real-time data.
And understanding and monitoring these incredibly complex patterns, especially over water, must require some pretty sophisticated analysis. It actually reminds me of the kind of work our sponsor Embersilk is doing. If you need help with AI training, automation, or just figuring out where AI agents could make the most impact for your business, you should check out embersilk.com. So with this high frequency and the risk of misclassification, what's the latest in terms of tracking and understanding them better?
The progress is really exciting. Scientists are using new tools to study recent events, like a suspected immediate tsunami on Lake Superior. The big focus now is on integrating atmospheric data with deep ocean pressure sensors and tide gauges. Fusing all that data lets us definitively say, okay, that was immediate tsunami and not just a storm surge or a seisha. We're getting much better at it.
So what does this all mean for us?
It means we're really starting to solve one of nature's great puzzles. You know, that fact that only 3% are confirmed as meteorological? That just highlights a massive opportunity for discovery. As our monitoring systems get more advanced and integrated, we're going to uncover just how often these fascinating weather-driven waves truly shape our world. It's a great example of science constantly improving our ability to understand and thrive in our environment.
If you enjoyed this deep dive, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.